So welcome back. I figured out what happened with the crash last time. There's a bug in my screen recorder. If I switch those desktops or whatever it's called, like the whole virtual screen, it crashes every time. So I disabled that with a swipe because I would do it reflexively, but I disabled it so it should be okay this time. In the meantime, I'll have to bug report that. Okay, so last time we were talking a bit about speculative execution, and I was showing this example toward the very end. I think we'll take a closer look at that again. Before we do that, I dug up a schematic that I didn't draw, which usually is a good thing. This one is from the Intel optimization reference manual. So Intel has these enormous, great documents, one that talks about just the entire instruction set, and it's like 3,000 pages or something. There's the optimization manual, which is a little more condensed, but it talks a lot about like how the machine works. So you could probably get most of what you get out of this class reading both of those, perhaps. We should make a textbook next time, a 3,000-page textbook. Anyway, I thought this one is a pretty good resource. So here says something about how this how the core works. So maybe we start up here somewhere. There's an L1 cache for data, but it's also an L1 cache for instructions. That's why instructions run fast, right? At least if you're running a loop, it's not like we're fetching instructions from memory all the time. These instructions are x86 kind of instructions. They're not actually what the CPU sort of operates on. Many of those instructions are quite complex. It'll be like a multiplication of a memory operand with a register. And you don't directly operate on memory in any sort of CPU. You would have to load the memory contents first and then apply the operations. And so that's what's going on here in this decoding. Well, I don't know why there's several steps. Who knows? But anyway, it's decoding this rather complex instruction. There's much more complex ones than just a multiplication with a memory operand, but let's use that as an example. So now that becomes several micro operations. You would have a load from memory, and then you'd have probably a multiply, and perhaps you'd have in this case, I think that's probably it. Or if you, yeah, let's leave it at that. So now we have two micro operations that came out of one actual x86 operation. I think in a RISC CPU, I never took a RISC architecture class, and I never really looked much at RISCs because nobody uses them. But in those, I think that you wouldn't have micro operations because they're already such primitive instructions, so you would have to load it in first and then execute it. So in essence, the x86 CPU is a RISC CPU. It's just that it's actually on the fly interpreting this complex instructions into a smaller set of less complex instructions. Okay, so now we have these micro operations, or if you want, the RISC instructions. And from there, now we're doing this renaming and such, right? The assembly says, oh, move from that number, from that address into this register, but we don't really care about which register. The CPU doesn't care about that. It just kind of remembers what we meant by that register. It's treated as a variable. So there's this renaming buffer of some 100 or so entries where we can stick whatever we loaded into one of those entries. There's also some other things going on. If you're trying to load from memory, it's going to take a while. It'll probably involve, so it involves making room for whatever you loaded. Right? So that's part in the buffer, sorry, in the rename buffer. But then you probably also need space for the cache. So we're actually trying to load a 64-byte cache line It makes room for that. That's a load buffer first. That's coming in somehow, and I'm not exactly sure with the details at the moment. But anyway, for every load, there's a load buffer allocated. For every store you're making, there's a store buffer. It's holding on to stores. Remember, that's for making sure your speculative execution actually doesn't become visible too early. And also to make sure that any stores appear in the order they should appear, even if you run them in the wrong order. That sort of thing's going on in with these store buffers. So here we're running everything in order. We get all these instructions coming in order. We're deciding on store buffer allocations and getting the naming right of everything with the register renaming and so on. But after we're done with that, now we've sort of decided in which order all these things will appear to the exterior world, whatever's outside the core. Basically, that's whatever ends up in memory. So after that, you can run the things kind of any order you want, as long as you have any satisfying any remaining dependencies, like, oh, this load has to happen before this add. So then we have a bunch of instructions that we just need to run. And those are executed out of order by the scheduler. So it sees like, oh yeah, I have all the dependencies for this instruction. And by the way, I happen to have an ALU available, so I can do my add. So let me run that add on the ALU. I have both operands, and now an ALU became available. So here we have that one. Okay, and then maybe I wanted to do a division. I can run a division at the same time, because here's the divider, a floating point divider execution unit. I don't know where normal integer multiplier and I think integer multiplier on both of these and integer dividers on port 0, but it's not on here, I don't remember. Anyway, so it's trying to get everything running sort of out of order. There's 2 loads. We can do 2 loads per cycle. We can do, here in this particular architecture, this is the Sandy Bridge. It looks like we can do 3 ALU operations like adds and such per operation. It all depends on which exact family of CPU you're running on. There's another piece here. It's the branch predictor, and that's what's providing this support for speculative execution. So all of this, we're running instructions that we know we can run. Like we have all of our operands for a condition, or maybe we've evaluated a condition already for the branch, then we can just do it properly. But if we don't know what the condition for a branch will be right now, then we still want to load some instructions in, because there's a lot of work. So we want to load all these instructions kind of speculatively to see, yeah, probably that condition will be true. Probably the while loop will continue going. So we'll just load the next instruction and the next one and just pile them into the out of order execution window. Of course, all of that will be marked saying this is speculative until further notice. So the branch predictor chooses one of the 2 branches. It doesn't like try to execute all the different possible branches. That's just way too many. So it always decides like, oh yeah, maybe we'll continue around the loop, or this is the 4th time we go around. Probably it'll exit after 4 times. Something like that. So it all depends on how sophisticated the branch predictor is. You may have heard of HyperThreading. That also fits in here. Maybe we'll take, yeah. So HyperThreading is this idea of running 2 hardware threads on the same core at the same time. So there's only one core. All of this is exactly the same with HyperThreading. But we, instead of fetching one sequence of instructions, we kind of have 2 instruction pointers. And maybe we alternate between the 2. And we say, OK, let me read one instruction from that pointer and one from that pointer. predicts and so on, do everything in that order. And then for our here, the renaming and such, now we of course have to keep track of there's some more state keeping, I suppose. Like you keep track of 2 orders of execution, so you need to know like keep the dependencies separate. Like the EAX for this thread is not the same as the EAX for that thread, but the amount of resources you need is actually about the same. They just split the register renaming buffer in half. And so then, if you're running 2 threads, they can have half as many register values in flight at the same time. Same thing for the out-of-order execution window, which is kind of hiding in here somewhere. They would, I think, it depends a little bit, but I think for that one, they would also split that in half. So each thread can have about 80 instructions in flight instead of 116 instructions in flight. And that's why when you run with hyperthreading, each thread goes slower. They have half as many resources. Here, you want to execute the micro operations. They're going to have to share. So the scheduler says, okay, I have 2 sets of out-of-order executions that need to be done. So let me use a couple here for the first thread. And then if the first thread is done, like there's nothing more it can do, well, maybe we'll run a couple of loads for the other thread. If we haven't used up all the execution units, we can kind of pack in more. So that's a real nice benefit of hyperthreading. There's 2 threads that have almost no dependencies, which means you probably can kind of fill the execution units better. On the other hand, you don't get to speculate as deep as you would. You don't get to keep as many values in memory as you would, so each thread would tend to block more often. Like, okay, I can't make any progress until that other move comes in, and I don't have room to continue speculating. But then we're running the other thread. So there's a fine trade-off there, and if you've ever tried to run your favorite game, let's say, with or without hyperthreading, you may have noticed that oftentimes things run slower with hyperthreading. It all depends on the program. If the program runs threads that are kind of tightly interacting, then you lose all the benefits of having 2 independent threads, and you don't really, well, in the end, you end up with 2 slow threads that are waiting for each other. That's a poor choice. But if they're really independent, and ideally, if they're doing very different work, like one of them is heavily working on this side of the execution units, and the other one is just doing a big fat mem copy. And that's a beautiful thing to run next to each other. So one is doing computation using mostly these, and one is doing a mem copy using mostly these, then you would basically get twice the throughput. Yeah.
Is the system smart enough to try and pick 2 threads that seem to be doing 2 different things?
Absolutely not. First of all, the system doesn't know what the threads will do in the future. And then doing this at this time scale is hard. It'll take a lot of work, and then everything gets slower. And so it would be up to the application developer in that case to say it's called CPU Affinity. You can say like, oh, this thread should probably run on the same core as this other thread. Right? Things like that you can play with. Maybe we'll do a little CPU Affinity later on. Okay, so anyway. Of course, there's many other pieces to it. The memory control here is very abstract, but that's stuff. I guess we'll talk more about that when we start doing multi-core computation. All right, so there it is. Let's take another look at our example of this out-of-order computation to just see what happened, because I thought it was a pretty cool result. See, I want to do this on frames maybe. Oh yeah. If you are if you started on the homework, I just uploaded an updated homework. There was one little bug. Someone asked a question on Piazza. There was a typo in the second part. It should have been 2 versus 2 opt, I think, and it said 1 instead. Anyway, that one's fixed, and then I also added the last little part of the assignment. Okay, if you're doing this, and when you're running perf or perf stat and things, your numbers don't look right, or you get a lot of like not applicable or not available sort of things, probably you're having a virtual machine issue. Depending on which virtual machine you're running, it's different on the Mac. Of course, if you're using VirtualBox or something, it will be different again. There's all sorts of different virtual machines. They don't all support these performance debugging counters, right? Or performance counters. So if you're having that problem with your virtual machine, it'd be a good idea to first find that out really soon, because you need those performance counters. If you have that problem, let me know, and I'll try to find one way or another that you can work on another machine to do these homeworks. Another solution is that you run Linux on your, assuming you have an Intel at least. If you have an AMD, I don't actually know that the counters are all the same. It should be okay. You can run native. So if you run native Linux on your machine, then you should have all the basic performance counters. What we really care about here is things like L1 data cache misses, and everyone tracks that. There's more obscure things that not everyone has. Okay, so that looks right. Too many open files. Come on. Seriously. Okay, that'll have to be enough. All right, so what was it? Speculative.c. And I think I even wanted to change this and say all right. Okay, so this was the program. Let's just try to compile it again. So last time I ran it on my Mac, and we saw something like 4 billion increments per second, which is pretty awesome. The server isn't as fast per core, but let's see what we get. Oh, and this was running with this interferer. Let's maybe not have the interferer. Yeah. Oh, this is actually, where am I saving this? Okay, this looks right. Okay, we'll do it one more time. Seems like it doesn't even want to finish. What am I doing wrong? Stop equals 1. Oh, no, but we're not running interfere. volatile. Huh. Okay. Could be we're having some curious optimization error here, but let's see. Probably, hopefully it's something simpler than that. What is it? While not started. Okay. I guess I have a older version of the program for whatever reason. Oh, that was, okay. I see, okay. Now it's fine. I was messing with this interferer thread, which we were gonna look at later, but now it should be okay. All right, okay, ooh, we got a negative count. Okay, good. So how many did we get? 2.5 billion increments in about 1 second. That's even a little better than I expected because it's a 2.2 gigahertz CPU. So we're doing, so what should we be getting? We could take a look at the assembly. I think that's always a good idea, always fun. And the function is called count. Here it is. Let's see, what are we doing? Is this count? No, it's got to be here. That's got to be where the real count is happening. Here yeah, this XORL here, that's setting it to 0. That's a weird way of setting something to 0. Okay, so here we're incrementing this register by 1. So that should be pretty fast. The test is parallel with this one. That's okay. These two ought to be back to back. So that should take 2 cycles, right? We have to do the test and then do the branch. But here's a tricky one. This move, a move from memory, this instruction pointer relative, something they do a lot in 64-bit. It's pretty nice. So it's a different offset. RIP, that's the address of here, right? So this stop will be a different offset in every place if you keep using it, but it's slightly faster. But anyway, a move from memory, no matter what, is going to take you some 3 or 4 cycles. Right. And then we're testing the value that came out. So that should take another cycle. And then we're branching back. There should be another cycle, so we should be at least at 5 or 6 cycles, and maybe we can run the add in parallel with some of this. 5 or 6 cycles. So how do we get to 2.4 billion cycles? Well, that's going to have to be this speculative execution. So maybe we start moving this, and then we don't care. I mean, this one we run in parallel with a move, that's fine. And then we don't care how this worked. We just figure it's going to be fine. We go back and we start moving the next one. So now we can do, probably in the next cycle, we can start moving the next one. Right? We do one move, and then again we do the next, because this is running in parallel with that. This is running in parallel with, well, I'm not exactly sure. But anyway, it looks like after one cycle, we're starting the next move. At some point, that's going to fail, right? But we're doing it many times, and most of the time it's true. So the CPU is always predicting that it's going to continue. And so in the meantime, we are keeping lots of alternative values for this RDX. Right? With the register renaming, we're saying RDX version 1, 2, 3, 4, 5, 6. Right? We have room for some 100 or so versions. So we go a few of these versions in. So it'll be 0, 1, 2, 3, well, 1, 2, 3, 4, 5, 6, 7. And then after a little while, we've actually done the move, right? And then once we've done the move, now we can do the test. And once we've done the test, and we know that this branch was true, so now we can actually retire those instructions. We had these speculative add instructions that kept happening for a while. And then like 5 cycles later, then we actually know, oh, okay, it's true. So then we can start running, then we can kind of roll forward a little bit, get rid of those older versions that have RDX lower than 2, right? So what we end up doing is doing one move every cycle, and then we're doing one add every cycle, and kind of a little bit later, we're rolling up the history of old versions, and at some point, this isn't true anymore. We do the test, we say, oh, shoot, I made the wrong prediction 20 cycles back. So now we have to kind of kill off all the intermediate results from 20 cycles back. So a whole bunch of these versions of the RDX, all of those get thrown out. We lose another 20 cycles because it costs 20 cycles to kind of do a rollback. It's sort of an average cost of a failed prediction. And of course, all the work we did is lost. All the work we did from the failed prediction and on. But so now we ran for a second doing correct predictions, managing to do an add every cycle, and then we lose, 20 cycles worth of work and 20 cycles of overhead toward the end. So in this case, it really paid off. So I wanted to try a couple of other things. So I'm actually running this other thread at the same time. And right now that thread is running on a different CPU. The scheduler is smart enough to do that. So it's the OS in this case is not the instruction scheduler on the CPU. That one isn't smart at all. But the CPU scheduler in the OS says, oh, this guy wants to run 3 threads. Fine. So I have lots of free cores. Let's use 3 different cores. That's all the scheduler does. And it might, I think when you start a thread, it'll get assigned to a core, and then every second or so, it reevaluates this assignment. Where should various threads be running? Okay, so what are we doing here? I'm just waiting for this interferer thread to get going, but it's not important what the interferer thread is doing right now. And then we're starting the count, and then we sleep for a while, and then we stop the count. Right? I'm having to use these volatile variables here, because otherwise the optimizer would say, here, let me just read the stop once before the loop, because the optimizer will always assume that everything is single-threaded. And if it's single-threaded, stop isn't changing inside the loop, so why should we be reading stop every time, stick the value of stop in the register, and then forget about it? Well, in fact, you can do better than that. We know if stop was false from the beginning, then we know it'll continue forever, so we don't even need to check it. Okay, but when it said, when you put this keyword volatile, that means that every time you read or write to this variable, you actually have to have a memory operation. So this is a read of stop, so that has to be read from memory. The same is true when we do a write, like I was planning to do down here. Okay, so I want to see what happens if we just, in this case, we start writing to this stop variable. And I think because it's volatile, I think that the optimizer will leave this alone and let it actually do a write. So, but we can easily find out. It would be enough to just run it, I think, to see how if it did. Okay, oh, that was really fast still. So it's probably not doing anything. Let's take a look. It's called interfere. Oh, here it is. Sure looks to me like it's running. Stop. Stop. Huh. What on earth? Oh. So this is really curious. Let's see. Okay, let me change this from stop to run. So I think what I was hoping would happen here is this other thread keeps writing to stop, and so it'll end up in its cache line, like it's in its L1 cache, which means it's invalidated from the other one. And so now this this loop here wouldn't be able to make very much progress because, well, maybe it could speculate for a little while, but it's only kind of 100 cycles, and after that it's in the wrong cache. So it's going to really slow down a lot, I would have thought. But now it seems like it's not doing anything. So I'm speculating that perhaps this here, this doesn't have an effect. The compiler decided it has an effect, and so that should be okay. Like it decided it has an effect. It is doing a write. Where is it? So this is the loop we're running. See, it's reading and then it's writing it back out. So this really should have that cache line slow down effect, but it doesn't. So I'm worried that maybe the CPU decided this doesn't have any effect. Yeah, so I thought we'd try a little experiment. There's a couple of things we can do, but the first one would be, instead of doing, this silly move which doesn't do anything, maybe we could actually increment it. So instead of calling it stop, we'll call it run, and then we can increment it by 1. So here, this one here is while not stop, right? So as long as it's not set to 1. But so we'll call it run instead, and it'll be bigger than, if it's bigger than 1, it's run. So we'll rename it to run. Okay, and then we'll do a run plus plus here.
We also have to be careful so if the overflow doesn't wipe it 0.
Not anymore. Oh, sorry. This one here. Yeah, it's kind of small. You're right. Thank you. Not anymore. Actually, how long would it take? Any guesses? What's that?
4.2 billion is the highest number which unsigned. So that's not an unsigned number. It's a signed. It was a signed.
Well, so we made it an unsigned long.
Yeah.
Actually, depending on which C compiler you're using, on which architecture you're compiling for, a long might mean 32 bits or 64 bits. I am a little unclear on the Linux. I think it's 64 bits, but now it's for sure 64 bits. The long. You could also say, I like that, the uint64_t, but then you have to include an extra thing. Okay. Okay, so how long will it take? Just roughly. Before we overflow this counter.
I think you have to remove the not signed equals.
Sure, yeah. Thank you. So, and then we should start at 1, otherwise we're going to stop running immediately. All right, but how long would it take before run becomes 0?
2-ish seconds.
2-ish seconds. Nope. Let's try another one. So we can do, let's say we're running this really fast, right? So we can do a couple billion increments a second. So I mean, in that sense, you're right, but you're missing a significant factor. It's a 64-bit value. 32-bit, we can finish in about 2-ish seconds. So how long would it take to do finish a 64-bit counter?
20 years.
20 years? Okay. I think you're low, probably, because it's about 4 billion seconds. Or did you compute it? No, no cheating. I don't know how many 4 billion seconds is, but it sounds like it's more than 20 years. 126 years, okay. Okay, well that's actually very close then. So you would get a point for that if it wasn't a test. Okay, so we're not worried about a 20-year or 120-year timeout for class. So, all right, so let's see. Do we have it all right? While run, and then we have to set this one to. This also isn't gonna work, right? Because now this interferer keeps keeps incrementing it. So I'll set it to 0 to stop running, but then it starts running again.
Can we join the interfere thread before you set it to 0?
I think maybe we'll do like this. Yeah, and so this got more complicated than I had hoped. But it's often like that, isn't it? Thread jump. Okay. Yeah, so that's the interferer. And here I want to stop it from interfering. Well, that one's also called interfere. That probably won't work. Okay, let's see. So now, all right, let's see. At least it compiles. That's a good start. Okay, what were we doing here? So while increment run plus. That's pretty incredible. Well, all right, maybe we should make sure that, did I do the right thing here? No, I wasn't. Aha, look, I was producing assembly. This might be different. Okay, yeah, here we go. So the time is always a second because we time it for a second, but so now we got 603 million instead. So it's still actually doing pretty well because we're, we're reading this value, and it's not even in our cache. So it's going to take us on the order of 40. If we're on the same, running on the same chip, it'll take on the order of 40 cycles or so to get it out of the L3 again, probably more. So the reason that this is actually running relatively quickly is that we're just speculating deeper. The CPU can speculate relatively deep, hundreds of instructions, and so maybe we kind of amortize or we don't see the full cost of all those cache misses. See if we can get it a little bit worse. So I'm going to bring this out here. Now I would imagine that this, even without the interfere, is going to get. Let's see. How do we? I guess I can say increment is 0 early on. Yeah. Okay, so we run this without the interfere. I just want to see how fast it goes first. What? Oh. Okay. I was really reusing names here. That's bad. Okay. Okay, so now we're getting only 400. Oh, yeah, okay, let's see. All right. Okay, so I guess I think we'll just leave it there for now. We can't dig arbitrarily deep in here, but there should be more interesting experiments we can do. I'll try to dig up one more for next time maybe. There's something called false sharing, which is a very important effect that we will certainly run into a lot later on in the semester. But we don't need to worry about that now. Okay, so anyway, we were able to do 600 million increments per second, 600 million, and each one of those should have incurred a cache miss that took about 40 cycles. So that's a speed up of 10 to 40 times. Let's see, 10, yeah, maybe 10 times. So speculation gave us about 10 time speed up in this case. You only get this when the branch prediction actually works. So when you write your code, one way to make sure that your code is fast is to try to write loops that are, that run for a long time, or try to not have if conditions that are true and false half the time. Like they're almost always true, and then sometimes you have a false one. Sometimes there's ways we can do that. All right. We also had this other program, and I prepared a little bit for the closest benchmark. So I thought we'd take do a revisit of that too, to see if we can speed that up properly. There's many things we can do to speed this program up. And we observed some of the problems last time, so let's see. So the way it worked was we say, I actually made a larger file now. We're going to deal with 100 million lines in a bit, but let's just do it with 10,000 lines for now. So the point here of this program, which wasn't, what it does isn't so important maybe, but it reads in the set of lines here. It treats them as just infinite lines, and then we provide a coordinate. And it scans through all the lines to see which of all the lines provided is closest to that coordinate. And so for 10,000 lines, that was really relatively quick, but I think if we run it with 1 million, now it's not so quick. And then with 100 million lines, then it's unbearable. So last time we ran perf on this, and we saw a couple of things going on. We eliminated that square root bit, right? The square root was a relatively big time consumption, but the main thing was this scanf. Just reading in all those lines was the actual problem. So this is, I think, sort of a common lesson in programs, well, just a common lesson overall, that the complexity of the program is not so important. We had this linear scan of our array. That's not so bad. What's really bad was just reading in the strings. And so the algorithm that we used, is actually not important. You could imagine having an R tree or something clever. R tree wouldn't work in this case, but maybe there's a clever algorithm you can apply if you're really smart. But if you're not really smart, then we can try this instead. Just make it faster to read in, and then have a brute force search, because brute force search is actually pretty awesome in many cases if you write it the right way. I had a student over spring break. Sudipto, are you here? No. He spent almost all spring break investigating how we can find the smallest number in an array. So an array of 256 values. Which value is the smallest one? How do you do that quickly? So there's many different ways you can do it. It turns out you can maintain a heap. That's log n. That's really awesome. Except it's really complicated pointer arithmetic and stuff. And so it turns out we could do just a linear scan much faster than a heap if you do it right. So hopefully we'll get to do a little bit of that later on. Anyway, what we were going to do here was see if we can speed up this I/O relatively easily. I think we can do that. It's not just I/O. There's, let's see. So it's hiding in frames closest. Okay, so here was the problem. We're reading in these things, and then we have to do it every time. So it'd be nice if this work that we do, we're given a text file. So what are we going to do? We're going to have to read the text file. Right? But what if we just kind of cache the results? Because next time we're using the same text file again. So what would be an easy way of caching the result of scanning, all this scanning? In this case, I was thinking we could, we could improve our line store a little bit. So this is the line store at the moment, just malloking some memory. So an alternative, so there's a couple of things going wrong here. First one is probably that for every one of these, we're mallocing a little struct. We talked about how to manage memory allocation. One very common thing that someone brought up the other day is that often, if you know that you have the same size, you want to allocate the same size over and over and over again, then don't keep mallocing that. It's called can be called a slab allocator. You just allocate a big fat array with lots of those entries, and then you manage those entries yourself. In this case, it's super simple because we don't free any entries. So let's just do that instead. So then it'll be like this. Okay, so I used to have 1 million pointers, right? 8 times, that was the size of a pointer. And now we're doing 1 million lines instead. So this line here, I changed it from pointer to pointer. Okay, so now we have space for the lines right there. That makes it a little easier. We don't have to do this part anymore. And then I guess we change our dereferences to periods. Okay, so now we're not using malloc anymore. So we already have a nice, probably a nice speed up. Let's see. Although it's so small compared to the I/O that maybe we won't even notice. But let's see. So this was the time before. Let's run it a couple times. Maybe there's a little benefit, perhaps. Try one more time. Yeah, okay. We shaved off a little bit, but it's not significant. Yes?
I was thinking you're doing line count plus plus still.
Mm-hmm.
But since everything's in the same array, should do line count plus the size of the extract.
No. So lines here is a struct line array. So if line count plus 1 would be the next line. Yeah. If this was a char array, it would be different. Okay, so that's a good start, but it'd be much better if we could just keep these results. So right now we're throwing them away every time. So what's an easy way of keeping all of this, all these parsed doubles so that we don't do it next time? For that, I like to use Mmap. So Mmap is just like malloc, except you could tell it that you should really map in the contents of a file. So if we have if the file is empty, if the file doesn't exist, well, then we have to create a file. But if there's a file there already, then we just get the contents that were there last time. So what we'll do now is we'll create a file. The first time we'll create a file, and we'll write into that file. But because it's Mmap, it just looks like memory accesses. So this part will be the same. But then next time, if the file exists, we'll just mmap the file in and then forget about it. Then we're done. So let's get a little more concrete. Okay, so I had a little, like a celebrity chef. Because that was a lot of typing. So what am I doing? I'm checking, does this line store cache exist? If so, we have a cache. And then we open up that file, and then we want to mmap in the file. So get rid of this, and we'll say, oh yeah, there was one little piece more. We'll do this one too. Okay, so here, if there wasn't a cache, it's actually Mmap gets a little upset. If you try to mmap in a file that is of size 0, and then you write to something beyond the size, Mmap doesn't grow the file. It just wants to map in an existing file. You're allowed to write to it, that's fine, but it doesn't extend it. So now I'm just making it the size that we want this to be. I don't know, I'll have to define them. Lines to, let's do it 100 million. Okay, so now we map this in. So all I did was here is I'm saying, let's go to the end of the file and write a 0 to the end. And yeah, oh, here I'm writing the 0. Okay. I feel like something's missing. Okay, but let's do one at a time. Okay, so now to map this in, we will say how big we want it. Oh yeah, this is where I want a +8 actually. And then we want to be able to write to it, read from it, and it's a shared. On this one, I'll explain in a bit, and we reading it from a file, and then finally our file descriptor. Okay, so we're telling the OS here that, oh, the contents of this file fd should appear, give me a pointer to the content of this file. So if you've taken 385 or any OS class, you may be familiar with how this works. By default, it'll just say, oh yeah, the contents of that file are at this address, and not do anything about it. And then when you try to read from some address, you'll get a page fault, and you map in a part of the file. And then you keep getting page faults. You access these different parts. You keep getting page faults. It's a little inefficient. If you tell it map populate, it'll read in the whole file right away, map in everything right away. There are no page faults. That's the only thing going on. Yeah?
Where do you declare have cache?
I don't. Thank you. So great to have a whole room full of code reviewers. Okay, so if we don't have cache, okay, so now we have a file, we've mapped in potentially an empty file, and then we probably should return have cache. Oh, and I think what I wanted to do was make the line count here. So right now we're writing in the, it's changed a little bit, right? So all of these initializations now, they end up in an Mmap segment, which will end up on disk at some point. The OS doesn't hurry it. Like, it'll just do it at some point before evicting the disk cache stuff, but it'll end up on disk at some point. But the line count is a little difficult. That's it used to be just a global variable that would be lost. We need to know how many lines are in the file too. So I was thinking maybe at the end of the whole thing, let's say line count equals lines like that. So now line count is a pointer that just points to the very end of this huge file. We'll stick our have an integer there that says how many lines are actually filled in our file, and then we have to do this. Okay, so I think if this, yeah.
Do we also need to start each of the local line counts?
Yeah, definitely. Although maybe we want to be really nice about it. Who cares? You know, we could have a local variable. On the other hand, I didn't call this volatile, so I think the compiler would probably do common sub-expression elimination and have a local variable implicitly for that line count. Was there another question? Sweet. Okay, let's see how far we get with just compiling this. Okay. I guess we want I think it's actually called or is it sysmman? And then it may be a Linux. It's not called Mmap, as I recall. Let's see. Feels like we're pretty close. I had a typo somewhere. What's this H line count?
The bottom one here.
There. And I think it's upset about this. This is probably hiding in file, maybe. Or standard IO, maybe. All right, we'll try that. So, oh. Okay. Sysmman. Where is that sucker hiding? Oh, is it maybe in uni std? Oh. Okay. Oh, this will tell us. This is so weird with man. Like, there's different sections of the man pages, and you never know which section stuff is hiding in. fcontrol.h, that's the one. Okay. Yeah, so to clarify, see, I was doing this man 2, then you get the one for the C. But if you say like that, now it's the one for the bash command. And then there's a 2 and a 3, and I have no idea what the difference is between them. I tried to figure it out at some point, but okay. So let's see if it makes. I think it does. Should we do the stat too? Make sure we there. Let's get that in there too. Line count equals. Oh yeah, that's okay. Of course, it doesn't like when you do that sort of thing, but this is C. Okay, so let's just make sure it runs first. Still runs, still slow, but that's because we're not doing anything with it. Like, now we probably have that. Let's see if we have that file, actually. Let me delete it first. Yeah. Let me delete that just to make sure. Line store. Do it again. Yeah, I thought it went a little too fast. Okay, so there it is. Okay, so now we're not actually using the cache. Every time we run it, we're running all this code. So I think we need to fix one more thing. That would be in this line store init. Oh, aha, read line. Okay, actually, maybe. Ah, okay, good. Why didn't it do it last time? Did I?
You deleted the file.
But I thought that the first time we ran it, after we fixed all this, it ran slowly. And that.
Did you read?
Oh, sorry. Yeah, of course. The cache wasn't there before. Yeah, sorry. I deleted the file. Every time the cache was there, I deleted the file. So anyway, so that's better. So now we're not spending much time on scanf anymore, but it's still kind of slow. So I think I want to delete this thing again, and then I want to do 100 million lines, and then you'll notice why it's slow. This probably will take a little while. So now it's preparing the cache. We're not worried about that. But I am worried about the computation. Once we've now, we have the cache, reading it in is really fast. Maybe the first time it's slow because it might be sitting on disk. It's not even in this cache. But the time after that, it's going to be fast to read it in. Let's not worry about that part. But we're still scanning 100 million lines. So there's a lot of work that gets involved in that. So while we're waiting for this cache to get populated, let's see what it does. Because I can't show you the perf before this is finished. Otherwise, it would go straight to the perf. Okay, so it's not this one. This is not the pair thing. That's the complexity is way too high. We cannot, systems folks cannot fix that thing, right? But we can fix the part where we're trying to get closest line. So here, right? We're running through all of them, and we were computing this line distance. And the line distance is actually kind of a complex thing. Here. This computation here, and hopefully this will be done shortly. This division here, divide by all this whole thing. That's a relatively complex thing if you want to do it 100 million times. We didn't used to worry about it because we had 1,000 lines. Who cares about 1,000? But now we're suddenly doing a whole lot of work. Okay, so to speed this up further, I wish we could see this in perf. Come on, finish. To speed this up a little further, we probably should be caching some of the work as well. Right? We can't change the user's algorithm, but we can stop the user here being an algorithm dude who wrote this from the beginning and then complains that it runs too slow once it's out for deployment. Right? So now we're running running this on a production system, and we're wondering like what's going on. Well, we have a brute force search over here. That's okay. We don't know any better way to do it than the brute force search, but maybe we don't have to do all of that work at the every time. As a little anecdote, I was performance debugging WordPress for part of the UIC websites. They're relying on WordPress. And I had never really looked at WordPress before. I had no idea. That thing, holy shit. So every time you load a web page, it reads in the entire WordPress program, which is PHP. So it's reading through all this PHP code, and then it starts loading templates and applying stuff. So if you have a few plugins in there, it can easily be hundreds of thousands of lines of PHP, which it reads in every damn time you load a page. So that's why it's slow. There is no fixing it, unfortunately. The only solution is get rid of PHP, but they don't like that. So anyway. It's not that PHP is slow, it's this execution model that, oh, we should load the entire environment every time someone wants to load index.php.
Are they caching even?
They cache some of the bytecode. They compile the code into bytecode. Anyway, this took 3 minutes. So let's run it the next time, now with a cache. Still slow, right? But a second is pretty okay. But where are we spending all our time? Yes, I got the password. Okay. Never get that right. Sometimes it wants it, sometimes it doesn't. Okay, so where are we spending all our time? It's always important to keep running perf, right? You always want to profile your code because you don't really know what it's doing until you measure it. You can have some ideas. Okay, so it looks like we're spending a lot of time in line dist and also a lot of time in line store.get. That's kind of surprising, so let's see what that's doing first, maybe. Okay, so this one, not much we can do about that at this point. Maybe we can worry about that later, but basically what's taking time here is moving from memory. So the problem is we have an array of, each line is 24 bytes, 32 bytes, right? And there's 100 million of those. So that's 3 gigabytes. And even if it's sitting in RAM, we still have to blow through it. It's going to take a while. It's not instant. So in order to fix that, I think we need to split it between multiple CPUs, probably. We could try to shrink the data, maybe. There's things we can do, but that one's kind of difficult. Let's take a look at the other one. Line dist, about the same amount of work there. Actually, what is this one doing? Oh, that's also running line dist. Okay, right. Sometimes I don't really understand the reporting here, but okay. So let's see what line dist is up to. There, it's our friend the divider again. For whatever reason, division is really hard. This is floating point division. It's nowhere near as hard as integer division, but it's still much worse than floating point multiplication. I think I read 16 cycles or something like that. And we're doing many, many, many of those. So that was one of them. I think we ought to have been using, no, line slope, that was for the other one. Yeah, so line dist is the only one we're using now. Okay, so can we get rid of it? In fact, there's more we're doing here. We're doing some multiplication too. Those are also slow, but you can't tell because everything's backed up on the single division execution unit that we have in the CPU. It's extremely busy. And we don't have the time, but we could measure that exactly. We could see like, oh, how many cycles was the division execution unit busy during this whole run? And we'd find out that, well, every one of them, pretty much. Okay, so let's see if we can get rid of that part. So this code here, the dx and dy, it looks like this only has to do with the line itself, not with the point. We can't do much like with a user-specified point. We can't really cache that, right? But these are the lines. This is computed from the line. So if we call it like this instead, let's not do any division at all, of course. So we multiply by 1 over. Right? So if we can compute this reciprocal once, and then we can multiply by this, now we don't have those two multiplications, and we don't have the division, and we don't have the sum, and this should be awesome. So, but then of course we'd have to pass in the reciprocal. And where can we get this from? I think line store can help us out. So, oh, sorry, I was practicing. It's already there. I should have removed it. Okay, so in add, why don't we compute the reciprocal? This isn't quite right. So it should be x2 minus x1, and this one is y2 minus y1, and then the reciprocal one divided by dx times dx plus dy times dy, right? That should be fine. And then, of course, we want to pass in the reciprocal. Let's see where we have it. There, so line dist, we'll have to change that. Yeah. I had one of those too. But anyway, let's change it here. So, and finally, L dot reciprocal. Okay, let's see if we can get it to compile at least. Now, I'm afraid we're out of time. Line dist. Where's the other line dist? Oh, there. Pretty good. Why does it want? Let's just redo that. I had another target too. That was. Okay, so we have to remove this cache. What's it called? Line store. Yeah. Okay, so we can run this again, but we're out of time. If you want, hang around and see it run. If not, we'll do it after. Okay, I'm going to start this. All right, so that's it for today. I posted the updated homework. Please get started. Let me know if you can't get your perf to work. It could be your machine's fault, could be your fault. And so talk to me or to the TA. And have a good weekend.